So some of you were asking me during the school that if I am also a professor. So that question is answered by Sushmita. And the one question that you were asking today, that what about the fairness in matching, right? So let's see some of the fairness notions here. So what is unfairness that you see today in the stable matching? Either it's man optimal or it's women optimal, right? And when we are talking about man optimal matching, we know that it's worse for women, right? And when we are talking about women optimal matching, we know it's worse for men, right? So for example, maybe this was one of your tutorial question as well. So if you look at this example, right, and here if we look at red matching, it is man optimal and worse for women, because men both are getting top preferred person and they are getting the second preferred person. By the way, these numbers denote the rankings. Okay, so for this guy, this is the top preferred girl, and for this is the second preferred, and so on and so forth. Okay, so and if you look at this blue colored matching, then this is women optimal and worse for man, right? And we don't want such a matching. Okay, we would like to treat each individual equally. Okay. So one of the fairness notion is egalitarian stable matching, and this will be the focus of today's lecture. Towards the end, I will introduce a lot of other fairness notions, but we will not talk about that in detail.
But in that case, we could not have done anything.
Meaning?
Like in that case, where two men.
Let's see. Okay. So you're right. So let's look at two notations. MR MW is the position of woman M in men M's preference list. Okay. So when I'm talking MR, meaning I'm talking about men's ranking, and MW. Okay. So position of woman W in men M's preference list, right? W or WM, position of men M in W's preference list. Okay. Okay. And this is the egality. Let's say mu is a stable matching, and this is the egalitarian cost. Okay. So what is it? See, look at a matching edge, okay, and then let's look at W's position in M's preference list and M's position in W's preference list. Okay. So one thing to note here is that the graph is not complete here. It's not a complete bipartite graph. Okay. So every man need not rank all the women, and so on and so forth. Okay. So Gale-Shapley algorithm still gives you stable matching. It's just, of course, it need not be perfect now. Okay. The matching will be stable. Okay. So now because it's not a perfect matching, there might be some men or women who are unmatched. Okay. So for them, that's intuitive, right? That the egalitarian cost will be, this notation is for preference list, okay, +1, because this is unmatched. Okay. So is the definition clear to everybody? This is the
set V of mu.
Yeah, vertex set of the matching edges. Okay. Is the definition clear to everybody? This is the main definition we are going to use. This thing, this part.
So egal mu is some like notation that we are
Egal mu meaning egalitarian cost of matching mu. Okay. This has nothing to do with the stability. Okay. Now look at a matching edge. Okay. MW is a matching edge. Mu is a matching here, right?
Yes.
Okay. Now look at M in W's preference list position, W in M's preference list. Okay. Sum it, right? Look at the, I can also use the term agent. Okay. So look at X, which is unmatched. If it's not a perfect matching, there might be some people who are unmatched. If it is not, then it's fine. Okay. Let's say there are some people who are unmatched. Okay. So just think of it that if someone is matched to the last person, right, then what will be the contribution? Length of the preference list, right? So this +1 is to capture that it is not matched. Okay, okay, fine. Let's look at an example. Okay, this is our goal, to find a stable matching that minimizes this cost. Okay, so let's say this is a small example, and let's say this is man optimal matching.
Why did we want the function to be like that? Like in egalitarian, what is egalitarian in that we are?
Because we want to minimize. That is the purpose. That is the meaning of basically egalitarian. Okay. So okay. So actually, the name according to me should be utilitarian, but historically the name is egalitarian. Okay. So do you all see that it's a man optimal matching? Right? It's very simple. Everybody is matched to the top preferred women, so of course it's a man optimal matching, right? Okay. Now let's look at the egalitarian formula. Can you all compute the egalitarian cost of this matching? For the first edge, let's say, what is the contribution? 5, and you can notice that for every edge 5 is the contribution, right? And there is no unmatched agent. Okay. Let's say I had one M5 also, then of course that will not be matched, so that would have been something, but in this example there is no unmatched agent. Okay. So what is the egalitarian cost here? 20. Okay.
So this one is within the bracket, is it? This prefix plus 1 is.
Yeah, this is the bracket. Yeah. Okay. So for man optimal stable matching, this is the egalitarian cost in this example, right? Let's look at women optimal matching. What is the egalitarian cost? Same. Okay. The example, okay, something happened with my this thing. Okay. So now let's look at this matching. Can you compute egalitarian cost for this matching? M1 is matched with, this is neither man optimal nor women optimal matching. This is, but you can first verify that it's a stable matching. Is it a stable matching? All of you are convinced? Are you convinced as stable matching? Okay, now let's compute the egalitarian cost. Okay, so it is stable, right? There is no blocking edge. Is there a blocking edge? I mean, fine, it's a small example, you can easily compute it, right? Okay, believe me that it's a stable matching, okay? Now, let's compute the egalitarian cost. 4 times 4, right? For every edge, what is the contribution? 4. 2 here, 2 here, right? 4. So, egalitarian cost is 16. So, now at least now we are convinced that there are stable matchings which are neither man optimal nor women optimal, something in between, right, because you saw lattice structure, something in between, and the cost, egalitarian cost is less. I am not claiming that it is the minimal possible cost or anything, it is just to show that there are stable matchings whose cost is less, egalitarian cost is less. Okay. Any questions? Okay. Okay. So, when we talk about the bipartite graph, because so far we are talking about the bipartite graph, we can find egalitarian stable matching in polynomial time, okay. And the kind of examples you saw since morning in bipartite graph, we usually call it a stable marriage, okay. Okay. So, these are the toolboxes we need to design this algorithm, okay. I will define one by one. So, male oriented shortlist, rotations and ST cut. How many of you are aware with ST cut, graph theoretic problem? Okay. So, I assume that actually everybody would know this, but fine, I will define it, okay. So, I love this algorithm because of the fact that, see, it looks very different, that we have some kind of preferences and everything, right. And suddenly, because of some nice properties of rotations, we can reduce it to a classical ST cut problem, which is already known to be polynomial time solvable, okay. Suddenly your preferences and everything will disappear, okay. So, let us define, sorry. So, male oriented, we will look at the example, but it is just that you remove M from W's list, preference list, and W from M's preference list, because this is always symmetric, right. If a man is present in W's list, then W will also be present in that particular man's list, right. Okay. So, if we want to remove, we will remove in both the list if W's current partner is better than M. Okay. Let us see an example. Let us say this is our stable matching. Okay. Now, if we look at W1, right, M6, the current partner of W1, right, is better than M1.
Can you repeat what did you say?
M6 current partner of W1, right, is better than M1, M2, M8, M4, right. So, I will delete all these from W1's preference list. Okay. And if I delete them, I also need to delete W1 from,
there.
exactly. So, I will delete that as well. Okay. So, here this is called basically the truncation, and here we are dropping, okay, and do it for everybody. Okay. So, this is how we get the male oriented shortlist. Okay. See, I am also using that everything starts from the man perspective. Man proposing algorithm we start with, we are talking about male oriented shortlist and all these things. Everything will again reverse if you start doing things from the women's side. Okay. Okay. So, do you think it's just a coincidence that man's partner is at the top in the shortlist and women partner is at the end in the shortlist? Is it a coincidence, or is there some property that it will always happen? Correct? So, that there it is very clear because we truncated like that. But what about this? Why W5 is at the top?
Because you didn't get the acceptance from the
Because whatever was in the beginning, right, M1 was rejected, right. So, for those women M1 is at the after the their partner. Okay. So, it is not a coincidence, this will always happen.
This is for a stable matching which was obtained from GS.
GS meaning?
The GS chart.
Doesn't matter.
Any stable matching if you do this.
Yeah, doesn't matter. This is because of the our truncation process. Okay. Okay. So, male oriented shortlist, is that clear? That's all. Okay. Second toolbox is rotations, right? And it's why that picture? Because it's really a engine for stable matching algorithms. Okay, lot of algorithms have been designed using this toolkit. Okay. Okay. So, again I need to define a couple of things. So, let us say mu is a stable matching, right. Now, what is successor of a man M? Okay. This is the first woman in man M's preference list such that W strictly prefers M to her matched partner in mu. Okay. What do I mean by all these things? Let us look at this again short list, because it is just easy to visualize in a short list. Okay. So, because we are looking at short list, you know what is the matching, right? M1 W5, M2 W3, M3 W4, so on and so forth. Okay. Tell me, what is the successor of M1? Successor is women, how it can be M8?
W8.
W8.
Because the other things we have deleted and what remains.
So, yeah, but let us first apply the definition. You are right, but let us first apply the definition. Okay. First women W in man M's preference list such that W8 strictly prefers M1. Okay. Okay. So, this definition, for this definition actually we do not need shortlist, this we could apply in general as well. Okay. But if we look at shortlist, there is something nice. What is nice? You are saying? It is always the second. Okay. Again, it is not a coincidence. You see, right? If I look at the short list, it is always the second person. So, it is easy to find successor now once I have short list. Okay. So what does the definition say? It is the first women in in man's preference list, okay, such, and it's not the matched partner, okay, after the matched partner. W8 should strictly prefer M1 over its current partner. Okay, look at W8. Current partner is M3, M1 is more preferred than M3. Okay, and why will it be always at the second position?
Because if M1 has W8, then W8 definitely has M1 in its short list, and it won't be the last because they're not
Exactly. Otherwise, if M1 is after this, right,
have deleted.
then we would have deleted. Correct? Good. Okay. So, again it is not a coincidence. If I look at the short list, it will always be at the second position. Okay. Okay.
Can you go one step back? Can you show for some? No.
Sure. Yeah, this.
Yes. So here, say we are taking for M3.
Okay.
Okay. So for M3, the first one would be W5.
Correct.
So in W5, now I check that. So what was the last one? Reference list says that W strictly prefers M2 or matched partner in mu. So W5 is matched with M1, and okay, it likes it better. It's what it-
Actually, I have an example where we will not have short list, right? We will have preference list, and then also we can apply this definition. But in case of short list, it is always the second person, right? Because if it appears here, it means of course this person prefers M1 over the current partner. Otherwise, we would have truncated, right? Okay. Okay. So next thing I need next. Okay. So what is next of M? Matched partner of successor of M. Okay. Okay. So is this clear? I have not had example of it, but you understand what is the successor of a man, right? Successor is always of a man is always a woman, right? And next is her current matched partner. Okay. Okay. Now let us say I have this ordering. Okay. This is with the modulo R. Okay. These are the matched agents. Okay. M0 W0 is part of my matching mu, M1 W1 is part of mu, and so on and so forth. Ordered list of pairs in a stable matching mu, okay, such that Mi plus 1 is next of Mi. Okay, it is just such an order. I am not saying that how to find it and so on and so forth. Okay, it is just such an order with this property. Okay. Then we call it rotation. This ordering is called rotation, that is all.
If such an ordering exists, then it's called a rotation.
Yeah, if I have such an ordering, that is called rotation. This ordering itself is, this row is called a rotation.
It need not exist.
I don't care, then there is no rotation. Okay. This ordering itself is called rotation. If you have an order, you call it rotation, that is all. Okay. Is the definition of rotation clear to everybody? It is just an ordering of matched pairs such that Mi plus 1 is next of Mi, that is all. Okay. Okay. Now, what is this? This is called rho is eliminated in matching mu. Okay. And what will happen? So, not everybody is here, right? So, whoever is not here will remain matched to its current partner, okay? And Mi will get matched with Wi plus 1. So, if I try to eliminate this rotation, M0 will be matched to W1, M1 will be matched to W2, so on and so forth, and Mr minus 1 will be matched with W0, okay? So, basically if you notice what is happening here, everybody is getting matched with its successor, right? I mean in this rotation.
with W1 and so on? Why are we doing this? What?
This is the definition of, this is how we eliminate the rotation. This is the meaning of eliminating the rotation. Okay, that whoever is part of this order, right, will get matched with its successor, right, and who is not part of this thing, right, will remain matched to current partner. Okay, exercise for you. Yes.
Can there be more than one this set for us?
Yeah, it can be.
And we'll do this for each of those.
We are not doing anything so far. It's just a definition. Okay, I'll come to the algorithm. Okay, I said, right, there are 3 toolboxes. So we are first trying to understand what are those toolboxes, and then we will talk about how to use it for our purpose. Okay. Okay. Now exercise for you is, I think tomorrow we'll not have time, but 10th is my day, so we'll do it on 10th. Okay. So prove it that when you eliminate a rotation, you will again get a stable matching. Yeah, mu is a stable matching. So you eliminate this, right? This mu, this matching also will be a stable matching. Okay. And one thing I am telling you that, and you try to observe it, that here in this man will get, actually you can understand. So we are matching it to the successor, right? So man is getting worse as compared to earlier, right? But partner of women is improving, right? That's easy to see. Okay, there's nothing to do in exercise here. Okay. So so far so good. Any questions? Rotation is clear to everybody, right? Okay. So this is called elimination of rho from mu. Okay. Can you give me a rotation in this matching? In this, yeah, with respect to this matching and short lists?
M1W5 first.
M1W5, yes.
And then M6W1.
What are you saying? M1?
W5. And then M1, oh sorry.
M3W. M7W.
Okay, let's first, are we not done? Is it more? Are you telling me new rotation, or are you asking me to continue? Okay, let's see if it is a rotation.
Yeah.
Okay. Okay. So M1W5, M3W8, at least they are matched, right? So that part is okay. Who is successor of M1? W8. And who is the partner of W8? M3, right? So M3 is next to M1. That part is okay, right? What about next of M3? Who is successor of M3? W5. And W5 partners is M1. Correct? So next of M3 is M1. So this is a rotation, right? Is that clear to everybody? Okay. So this is a rotation here. Yeah, and okay. So this will be a new matching. I don't know if this color is visible, but M1 partner will change to W8 and M3's partner will change to W5 and rest will remain same. Okay. By the way, you can tell me, is this color visible? Okay. Okay. Now, why do we care so much about rotations?
Because there is more fairness now. A woman has improved her preference and a man has his preference is reduced. So it's less man optimal and a little bit more.
So maybe if we keep doing it, right, we will reach to the women optimal matching.
Yes.
Yeah. Okay. That's right. But if we start with man optimal matching, do such kind of eliminate sequence of rotations, we can reach to our desired stable matching. Okay, and that's the purpose of these rotations. That's the use of this. Now you see how powerful this tool is.
Desired stable matching or women optimal matching?
Desired also you can reach, but you need to identify that the correct set of rotations. okay, and that is the hard part, right. What is a good set of rotation, like what is the set of rotation that is good for you, okay. Okay, okay, so this is the example. Okay, so this I have just copied from that green book. So, let us understand this notation. Okay, this is a man optimal matching, and what is this telling you, that first man is matched with women 5, okay, second man is matched with women 3, and so on and so forth, and this is telling you the position of those women in M's preference list. Okay, so for example, here M1 is matched with W5 and the position is 1. M2 is matched with W3 and position is 2, and so on and so forth. Okay, so this is my matching, and this is a man optimal matching. Okay, okay. So now here, now it's not that easy because it's not a short list. Okay, now can you tell me, it's the same, but try to apply your definition on this example. What is the successor of M1? Is W7 a successor of M1? W7 M1, right. So W7 is not, sorry, W1, no, right, because M1 is after this, right. W2, no, because M1 is after M7, her partner. W6, W8, okay, okay. So W8 is successor of M1. You see, it can, like, one person can be successor of many people, that's obvious, right. Okay. So these are the successors, right. Now what is next of M1? That's M3, that's clear, easy to find, right. Once I know the successor, next is easy to find, right, because I just need to look at the matched partner of successor, right. Okay. So this is how I can compute the all next. Okay, it is the same example, so I will not ask you again to find the rotation because rotation is same, which is M1 W5, M3 W, sorry, that is W8, M1 W5, M3 W8, okay, and if you eliminate it, this is the matching you will get, okay. Okay, so this is actually all set of rotations in this particular example, and the M7 is the woman optimal matching, but we do not need to go that because we do not need it. Okay. Okay. So this is something important, that every man women pair is in at most one rotation. Can you see why?
Because after doing that, the hierarchy has changed, right?
So once someone is in the rotation, right, its partner has been changed, right. So now the same pair cannot appear again, right, right. So but you can try to prove it more formally, but that is a intuitive description, right. Now because of this, that every man women pair is in at most one rotation, can I give a pound on the number of rotations?
Can you give a
Bound on number of rotations. Right? It's just simple, simple, n square, yeah, n choose 2. Okay, so it's not just that the number of rotations is bounded, we can also compute the all the rotations in polynomial time. How? We will not go to that, but we can find it in polynomial time. Okay, just not to confuse with, number of rotations are polynomial, but number of stable matchings are not polynomial. Think how, why, all these things, okay, think about it. Okay. So we can find it in polynomial time, okay.
So using the rotation, can we get to, like, there are finite stable matchings that are possible?
They are not finite. Stable match, that is a Stokes result which he said in the morning.
Finite.
Finite, yeah, yeah,
So
finite.
using rotations, we can reach any of those
Yeah,
stable matchings.
right, right.
So rotation leads to any of the stable matching that we want, the
Yeah,
number of.
right, right. Okay. Okay. So now we understand what is the rotation, right? But of course, one rotation is not going to give me desired matching, right? I need to find a set of rotation, okay, that is going to give me my desired matching, which is egalitarian stable matching in this particular case, okay. So, this is my first question, and my second question is how do we find it efficiently, okay. Okay. Let us say mu is a stable matching. So, let us see that once I have a matching and two matchings, what is the difference between the egalitarian cost, okay. So, if I have a, let us say mu is a stable matching and mu prime is obtained by eliminating some rotation rho, let us see what is the difference between the egalitarian cost, okay. Okay. Let us say this is my rho, okay. Clearly, matched partner of men who are not in rho does not change, right. So, their effect will cancel out. So, we only need to worry about people who are in rho, okay. So, this is the weight of rho, let us say. Now, what does it say? Just try to, okay, just stare it for a minute and then I will explain. So, what does it say basically? Earlier, Mi was matched with Wi, right. Now, Mi is matched with Wi plus 1, right. So, what is the difference? Whatever, but what is the difference, right. Wi was matched with Mi and now it is matched with Mi minus 1. What is the difference? It is positive, that is negative, you are right, okay. Egalitarian of cost of new matching is egalitarian of this minus W of rho, okay. Let us see an example. This is the rho naught, let us say, that we are trying to eliminate. Oh, okay. So, what is the egalitarian of this thing? Whatever is egalitarian of mu m plus what happened with the m1? It changed by 1, right? M3 changed by 1, right? Women changed by 2 and here it changed by 4, okay. Yes.
Can we say that for men it will always be 1 1?
No, it is actually no, okay. Yes, it is a bad example in some sense, but see, apply the formula, this thing, right. It will depend on the position of your successor, okay. Okay. So,
Say the success. No, the next will be the
Huh?
successor will be the second. For if it's shortlisted, then the successor is going to be the second.
But we are talking about the rankings in the original list.
exactly, ranking we should look at in the original, okay. Okay. So, our goal is to find, so if this is the cost, right, then what should we look at? We want to minimize the cost, right, egalitarian cost. So, I should look at this values as larger as possible, right, okay. So, I want to find a set of rotations of maximum weight, right. I know that I can compute all the rotations in polynomial time, let us compute it, okay. I can also compute their weight in polynomial time, let us compute it, okay. Let us just choose the rotation of all positive weights. Is this correct? Think for a while. If it is correct, then lecture is over.
Sequence would be negative.
Sequence matters, right. Okay. So, let us go to the picture we had. We had this picture, right. So, when I say that I will list down all the rotations, right, I will tell you rho naught, rho 1, rho 2, all those things, right. But can you apply rho 1 before applying rho naught? No, right. So, this precedence relations matter, right. I need to eliminate closed set of rotations, okay. So, just finding the set of all rotations and just then sorting and finding the maximum weight is not good enough, okay. So, rotations have precedence relation, that is the problem here with this algorithm, okay, which we are not able to capture, and the goal is to now find a closed set of rotations of maximum weight. So, closed set meaning that whatever rotations you had to eliminate before eliminating a particular rotation, that should also be in your set.
I didn't get it fully. So why are we after finding a maximum weight rotation? Our aim was to
This is a wrong algorithm.
no, that's
Okay.
the first goal. So why is that our interest?
Because you want to find a matching with the least possible cost,
Yes.
egalitarian cost, right? From I had a matching mu, right? I want to reach to a matching mu prime with the minimum egalitarian cost, right? Mu prime is my matching that I want to reach, right? What is the weight? Its cost is with respect to new matching, with respect to my current matching minus weight of rho, right? So if I subtract the larger quantity, then
It assumes that there is one rotation, big rotation, that will give me a jump from mu to mu prime.
okay, let's assume that set of rotations here. Even if you do that, right?
Yeah, he's right.
Yeah, it's a sequence of rotations. Yeah, it's not that every step is the maximum weight, or it's a, you can assume that it's a set of rotations. Okay.
Each step we are using.
I'll tell you the algorithm how to find such a set, but this is a set of rotations of maximum weight. Okay, this is what we need to find. Yeah.
Yeah, if we don't even have a closed set.
So okay, let's go back to this example. Okay, so suppose I list down all the rotations. Okay, and you can find the weight, right? Let's say row 3 is the rotation of maximum weight. Can I directly go and apply if I am here? No, right? Because that is not even eliminated, that is not even there, right? So there is a precedence relation that before row 3, let's say if you are taking this particular path, before row 3 you need to eliminate this, right? So all those precedence rotations should be in your set. Okay. So that's the general meaning of closed set, not particular to rotations. Okay. Okay.
So at each step you have to find set of all rotations.
Initially you will find all set of rotations, all weight, but this step is not correct. Okay, because finding just the rotations of maximum weight is not good enough for us. Okay. Okay.
It is not dependent on the configuration, right? If I have a current configuration,
Configuration meaning matching.
yes,
Okay.
and then I calculate the weight of a rotation.
Weight of rotation doesn't matter on that because it just depends on your original preferences.
Yeah, but if I eliminate or if I do a rotation and then I calculate the weight, will that
No.
weight be?
No. Because if you notice in the definition of weight of row, we did not use what is the matching. We just use their position in the preference list.
Right, but the list changes, right, once I rotate? Like the matching
No?
changes.
Matching changes, not the preference list.
So the weight will still remain the same.
Yes, weight of rotation does not depend on matching, it just depends on your preference list.
So why does the first algorithm fail? I can just collect all
But
the
that
weights.
that rotation was not exposed in your original matching. Okay. Can someone compute what is the rotation here? Huh? Diagram. Yeah, just list the pairs. It's not difficult. See? Definitely 1/8 is there because it is changing the partner. Just try to work it out, right? You know what is the matching. So what is the rotation there? And if you are lazy, you do not want to, right? Then also think that M1W8 is there, right? In that rotation, right? M1W8 is there. Okay. Is it here? So, you cannot definitely eliminate this. If you list down, then you will be able to see better, but if you are lazy, you do not want to list down, then just take it as a pinch of salt, right. That M1W8 is going to be a pair when you are trying to eliminate here, okay, but that is not there in the first matching. All the rotations cannot be eliminated there itself, that changes. And anyway, we saw that every pair participate is only one rotation, right? Okay. So, are you convinced now?
Yes.
Kind of. Okay. So, this is my goal now. Let us just focus here that this is my goal now, that I want to find a closed set of maximum weight. Okay. Okay. So, for this we will forget about what is the term, we will construct a digraph, okay, and then I will reduce it to the ST cut instance, we will define what is it, and then we will find ST cut and then prove that using that we can find maximum weight closed subset, closed set of rotations, okay. Okay. So, let us say now we are constructing this digraph, okay. So, let us say Vg is the set of all rotations which I could find, and that is my vertex set now, okay. Weight of a vertex is same as the weight of the corresponding rotation, okay. Now, we need to define edges carefully, now you need to pay attention here. These are rotations, I add edge rho prime to rho if, we will see at example also, but let us see this, okay. MW is in the rotation rho, okay, and rho prime is the rotation that moves M to W, right. One second, let us everybody, do you understand the statement?
So can you tell me M is matching or man, what is MW?
MW, if I am saying that this is a pair in the rotation rho, meaning at this point of time M is matched with W.
But it moves from
Yes. So, rho, that is the point, right. So, rho prime was the rotation who moves M to W, right. What does it mean? Then rho prime needs to be eliminated before rho, right. That is why, so this arc is basically capture, right, what needs to be eliminated before this, just before this, okay. We will see example also, but do you understand what is it trying to say? Okay. So, there are two types of edges. Rho moves M below W, okay, maybe let us first look at an example, otherwise you will be confused. So, there are these two type of edges, let us see this. So, we have vertices corresponding to rotations, okay. I have already computed weight, so I have written it, but we will share the slides and then you can compute it and check, okay. So, this we will call as negative node with the negative weight and these are positive nodes, okay. Let us say this is a rotation and this is what we want to add, but let us understand it, okay. So, what happened, rho naught moves M1 to W8, right, and M1 W8 is in rho 1, right. So, this is this type, right, MW is in the rotation rho and rho prime is the rotation that moves M to W, right. So, I will have an arc from rho naught to rho 1, right, because rho naught moves it to W8 and M1 W8 is in rho 1. Is this clear, this type of arc?
It doesn't say in how many steps, right? If I have like three things and if I do the rotation twice, it will
Twice
like if I
So,
have
this is
to-
one rotation, whatever you obtain, whatever this rotation did, the length of the rotation does not matter.
No, I think it's immediately exposed or exposed after some time.
Immediately,
Yes.
okay, immediately. Rho naught moves M1 to W8 at that is like rho naught did this thing, okay, okay. So, we draw an arc from rho naught to rho 1, okay. Let us look at type 2, what is type 2 trying to say? So,
I have a question. What do they mean by immediately before?
so they meant that I mean rho naught, then rho 1, rho 2, and then do we have arc from rho naught to rho 2? I think that is what I understand. That rho naught had to be eliminated before rho 2. Some for something, that's just an example. Then do we have arc from rho naught to rho 2 as well? But that definition, what does definition say of the arc?
Possible that M1 was moved to W8 by eliminating rho 0, but W5 gets moved to M3 at a later step by a different rotation.
Then from that rotation we will have arc.
Correct. So
Yeah.
rho 0 moves these two pairs,
Right.
edges, but the rho 2 or rho 3 where you're trying to get to, it has more people,
Yeah.
and those they are moved to their respective point by something else.
That, yeah. Okay. That's a, yeah. But if it happens with one pair,
Yeah.
then we add arc. Okay. Okay. So now if you see what happens with rho 1 moves M2 below W8. Okay, let's see here. What M2 did. Let's see what what rho 1 did. Rho 1 match M2 with W6, right? So it skipped in some sense W8, correct? Okay. Now what rho 1 is doing, rho 1 moves W8 above M2. So now why this happened, W8's partner was M3, right? Right? And it's suddenly going to M1. Why it happened? Right? Because what rho naught does, it moves W8 above M2, right? So if you start shortlisting, this will disappear, right? So this is why I know that, so these are called type 2 edges, okay? And an edge can be of type 1 or type 2, okay? So type 1, type 2, if you do not understand, like you don't need to go into what is called type 1, what is called type 2. We don't need that. You just need to know what is the rotation digraph, okay? You need to just understand this digraph is to capture what rotation is preceding the current rotation, that's all. This is to capture that point, okay? Did you understand the construction? Okay. Even if you are facing difficulty with construction, so just understand that this construction is to capture this fact, okay? So because of this rotation, I know that if I want to eliminate rho 3, then I need to eliminate rho 2, and if I want to eliminate rho 2, I should eliminate rho naught. I cannot directly jump to rho 3, okay? Is that clear? Okay. So this is the rotation diagram, this is called rotation diagram, it is used for other purposes as well. Now what is ST cut? Let us see. It is a pure graph theoretic problem. You have a directed graph G, a capacity function on every edge, and two special vertices S and T. Now you want to find a partition of Vg into two sets A and B such that S is in A, T is in B, and the number of edges, sorry, the capacity on the edges going from A to B is minimized. See, U to V, U belongs to A, V belongs to B, okay? Capacity on such arcs, edges, whatever you want to call, is minimized, okay? So this is the ST cut problem which is solvable in polynomial time. Now how do we reach here? Is the definition clear to everyone?
Does that mean number of edges is minimized?
Capacity. It is possible that there is a cut with less number of edges, but on those edges the capacity is large. But you can come up with another partition which has more edges, but the capacity is less. That is possible, right?
Is it find a partition or that's the right?
Huh?
The
question is, does the x is such that the cost is at most c for some c?
Oh, okay,
Yeah.
fine. So this, let's consider this as fine, this as that it is minimized. Okay, yeah. Was that your question, or your question was related to number of edges? Yeah, no, not number, capacity. Okay, and we want to find such a cut. Okay. So let's say this is our weighted rotation digraph, because type doesn't matter to me, so we have removed that. Okay. So all we care is what is the so this graph and the weights on these nodes. Okay. Okay. So let us construct an ST cut instance. So in this ST cut instance, everything remains same. Okay. The vertices in the original graph and the arcs, all those things are here. We add two new vertices S and T. Now S will have arc to all negative nodes. Okay. So negative nodes are here rho naught, rho 1, rho 3 and rho 4, and we have arcs S from S to all the negative nodes. Okay. Positive nodes will have arc to T. Okay. Now we also need capacity in the ST cut instance, right. So capacity on the original arcs, so this infinity is missing here, but on all the original arcs capacity is infinity. Okay. Whatever is the weight of this rotation, absolute value is the weight of these arcs. Okay. Oops, sorry.
The negative of into positive.
So that is the weight of this rotation. Okay. So weight of,
You're taking mod.
yeah. So for example, this is 1 minus 1, so we have this absolute value mod, as he is saying, minus 1 minus 1 minus 3, so everything positive. And from this also, this was anyway positive node, right. So whatever is the weight is the capacity of this arc. Okay. Is the construction clear? Okay. Okay. Now let us say K is the minimum ST cut in G prime. Okay. Now Pk is the set of positive nodes of G prime whose edges into T are not in your cut. Right. This basically means the set of positive nodes which are in the set containing T. Okay. And Pk and all nodes that reach to a vertex in Pk gives you maximum weight closed subset of G. Why, it is not at all clear, right. But let us first see what are we trying to say here, then we will also argue the correctness. So let us say this is our graph. Let us take any cut for now to understand what are we saying here, okay, because these two things have nothing to do with K, the construction has nothing to do with K, right. The minimum thing is required to argue the maximum thing here, that is all. Okay. Okay. So let us say we have this thing, right. So what is Pk, can someone say? Okay, what is K? What is the ST cut here?
All the edges
Name it.
going from A to B.
Name it.
S and rho 0, only that one.
Only that one, right. So this is the only cut edge here, right, its weight is 1, right. Okay. Now what is Pk? That is why I have this picture also. Okay, this picture is not very, this picture gives you information. What is the positive node here?
So one thing, row 2 was minus 1. Sorry. So we had somewhat 4 negative.
Yeah, but from this picture itself you can tell what was the negative node, but what are the positive nodes, right?
There are no edges into that's T, right?
I'm just asking.
No, there was.
Only rho 2.
So see, if you look at this picture, right, what do we know by the construction? That from S we added arcs to all negative nodes, and from all the positive nodes we add arc to T, right. So I mean, of course we can go back to the figure and again check, but
The definition of edge weights, how did you, the blue edge weights is just mod of what was this?
weight of that rotation. So, yeah, what is pk? Rho 2, right. So, set of positive nodes of G prime, that is only rho 2 here. Okay. Let us see the other condition, whose edges into T are not in your cut, right. Rho 2 T edge is not in the cut, where they are in the same set, right. Okay. So, pk is the rho 2, right. What is now this, what is reaching to pk?
Once again, what is G and G prime?
G was our rotation digraph,
Okay.
and G prime is the ST cut instance. Do you remember the construction?
Yes, I'm just parsing it.
So, from G, whatever you have in G, you have in G prime, first thing. Then you just add two edge vertices S and T, right. From S, you have arcs to all the negative nodes. From all the positive nodes, you have arc to T, right. Now, what are the capacities? All the original arcs, you have capacity infinity, right. On new arcs, your capacity is the mod of the weight of the rotation.
So on this diagram, can you please show what is pk exactly?
Yeah, so see what is the pk? So, this is our cut, let us say,
What is this bipartite graph suddenly?
this is a cut partition,
Oh, okay.
right.
Cut as a.
So, what is that, what is ST cut? You need to find a partition, right, such that you need to find a partition, let us say partition of the vertex at A and B, let us say, such that S is in A, T is in B, right. And now, what do you want to minimize? The capacity of the arcs going from A to B. Okay. So, when I am talking about this AB cut, actually this is minimum also, okay. But for now I do not care about, to define pk, I do not care about whether it is minimum or not, okay. I can define with respect to any cut, right. Minimum I will use to prove that this is maximum.
In this cut, there are some infinity edges also. That you
Yes, there are, these are the infinity edges, but there are no infinity edge going from left to right.
Oh, okay.
At least in this example there is none, and there will be none because of our construction. There will be always an ST cut with non-infinity. I will come to that, do not go jump there, okay. But first you understand what is pk and what is this thing, okay. Pk, just parse it, right. You do not need to read the full sentence. Set of positive nodes, okay. Set of, there is only one positive node which is rho 2, right, whose edge into T is not in your cut, right. Rho 2 T, of course, it is not in the cut because they are in the same set, right. So, you can define in both the ways, okay. Okay. Now, pk and all nodes that reach to a vertex in pk, right, which is rho naught here, right. So, if I look at this thing, right, now we want, so we want to say that because I have said that whatever reaching to rho 2, clearly I have talked about the closed set, right, set of closed set of positive rotations, right. All I need to argue now that if it was minimum cut, then this is max weight thing, okay. This is what we need to argue. Is this clear? What do we need to argue? First of all, is the construction clear, that how will we find our set? Forget about the argument, like forget about the proof for now. So, what is our algorithm? Okay, it starts like this. You first find out all set of rotations, okay, which I can do. Forget about the even complexity for now, okay. We will talk about that later. First, you find all possible rotations. I can find it no matter what is the time. I can find it, okay. I can find the weight of rotations. The formula we know. Using that formula, we can find the weight of rotations, okay. Next thing is construction of the rotation digraph, right. So, whatever type 1, type 2 edges are there, we will find it. Okay. We have rotations, we will apply those rules, we will find the rotation digraph, right. These 3 steps are clear. Now, I have a rotation digraph. Okay. Now, given that rotation digraph, I will construct an instance of ST cut problem. Okay. What is the ST cut problem? We have input as a directed graph, 2 special vertices S and T, and every edge has some capacity. Okay. Now, my question is, find a partition of vertex set A and B, let us say, right. What is the question? Find partition of vertex set A, B. Okay. When we say partition, it means okay, S remains here, T goes here. This should happen. I am talking about such partition only. Okay. Now, rest of the vertices, there is no restriction, they can go wherever they want to go. Okay. But what is my objective function here? The capacity, total capacity of the arcs going from left to right is minimized. Okay. So, this is our ST cut problem. Okay. I had a rotation digraph. Okay. Now, using that, we want to construct instance of ST cut problem. Okay. How did we construct? Whatever rotation digraph was there, just take it. Do not put the weight on the vertices, because ST cut problem do not have weight on the vertices. Okay. Just take the same set of vertices, same set of arcs. Okay. Then you add 2 special vertices, because we need that in ST cut instance, right, S and T. Okay. From S, you add arc to all the negative nodes, from positive nodes you add arc to T. Okay. Now, in ST cut instance, what else do I need? Capacities, right. Original arcs, put capacity infinity. On all the arcs, newly added arcs, capacity is absolute value of the weight of the rotations. This is clear? Okay. So, I had a rotation digraph, and using that I constructed instance of ST cut. Okay. Now, minimum ST cut I can find in polynomial time. Okay. Now, you find minimum ST cut. Let us say this is my minimum ST cut. Okay. Using that, I will give you set of closed rotations. Maximum weight, forget about it. I will give you set of closed rotations. We will argue it later that that particular set will be of maximum weight. Okay. So, what is my construction? You had ST cut. Look at the set of positive nodes that lie in this set, which is equivalent to saying this, right. Set of positive nodes whose edges into T are not in K, right. Set of, positive nodes that lie in this set, right. But what else do we know? We know that these are good, for some reason these are my good nodes, okay. But we know that we need closed set of rotations, right. So, closed set of rotation, if you recall the property of rotation digraph, right, why did we add arcs? To capture this precedence relation only, right. Seems suddenly excited, yes. So, yes, we added arcs to capture the precedence relations, right. That is why I am talking about the reachability set of positive nodes here that I have taken. You understand now? Why am I talking about this? Right? I have someone in my this path, because that rotation is important to eliminate before eliminating this rotation. This is how we have precedence relation. This is how we have arcs. Is this clear or not? We are almost done, so you can ask. Is this clear or not? Okay, is the construction clear?
Yes.
That how are we constructing this? Okay. Okay. So, what is not clear? Tell me.
Can there be more
More than one arcs meaning?
When we connect that all the nodes, PK and all the nodes that reach to the vertex in PK. So we are starting from S now.
What is S? Oh, S, this S. Okay, sorry, repeat your question.
So when we are basically we are creating the arc by connecting the nodes that touch PK.
Right.
That last line, PK and all the nodes that reach.
Reach to. So reach to, okay, maybe I should first say what does the reach mean. Reach meaning that look at a vertex in PK, right. So a vertex, reach to a vertex, this vertex V, there is a directed path. Okay. So let us say that is finally my set, yes. No, PK is rho 2, PK is rho 2 and then this both the elements will give me my solution, right. So when do we say, let us say V is in your PK, okay. Let us take any vertex U, okay. We want to see if U reach to V, okay. What does that mean? That there is a directed path from U to V, okay. Okay, let us look at this example only. Why am I saying that rho naught reach to rho 2, okay. Do we have a directed path from rho naught to rho 2? Do I have from rho 1 to rho 2? Rho 1 I can go to rho 4, but no. From rho 3? Rho 3 I will go to rho 4, but no. Rho 4? No. Okay. So rho 2 is only the vertex that can reach to, sorry, rho naught is the only vertex that can reach to rho 2. And the close set, all those things I am saying, that is to give you intuition why are we talking about this. We will argue it formally, why does it give you maximum weight and all these things, okay. But that is to give you intuition that, you know, why did we construct such a graph, why are we talking about the reachability set, okay. Because we added arcs only when it was required to eliminate this rotation before this current rotation, then only we added arc. Whatever were the rules, but that was the idea, right, that was the purpose, okay. You all seem to be lost. What is the confusion? Tell me. So where are you confused?
If I do rho naught and then rho 2, is it the same as eliminating rho 2 and then eliminating rho naught?
That is not right.
It's not right.
That is not.
We have to follow the direction. That's why we drew the arrows. Right?
Yeah. Right. And that sequence will be clear if I look at it. Okay. Okay. So why is this algorithm correct? Okay, maybe that will make it more clear. So currently we are just making some observation regardless of algorithm, okay. Let us say Q is some maximum weight closed subset of G, okay. Let us say Q is such a thing. The first observation is that any negative node in Q precedes at least one positive node, right, otherwise why will I eliminate it, correct. Because my, what was my this thing, function, egalitarian of mu prime is egalitarian of mu minus weight of rho, right. Now if something negative is coming up, that is increasing my cost, so why will I do that, because that is required to eliminate some positive rotation, correct. So that is why, do you agree with this statement, that if any negative is there, then it is required for some positive thing, okay. Okay, let us say P is my set of all positive nodes. S is subset of P and this thing denote the set of negative predecessors of S, okay. Now goal is this, agree, that maximizes this quantity, right, this was our goal, right, to find such rotations, right, okay. Now the same set minimizes this quantity, right, the thing that maximizes this quantity minimizes this quantity, right, because this weight of P is fixed, right. P is what? P is set of all positive rotations. This is fixed quantity, right. So, whatever maximizes it will minimize this quantity. Agree? Now, which is same as saying, okay. So, my goal now, if you notice, my goal was to find this, right, which is equivalent to saying that my goal is to find this, correct, because the set that maximizes this quantity minimizes this quantity. So, now I can say, okay, find me a set that minimizes this quantity, correct, okay, which is equivalent to saying this, right, P minus S plus weight of this quantity, okay, okay. Which one? Because yeah, this maximizes this quantity, right. Now, weight of P is fixed, something fixed, right, and this becomes negative. So, this is same as minimizing this quantity.
Okay, so you're based. Okay.
Yeah, right, yeah.
The same set minimizes there should be a plus before the. Okay, there's a bracket.
Yeah, there is a bracket, yeah. Okay, so my goal from here has been reduced to goal here. Okay, so now I want to find a subset of positive notes that minimizes this. See, there is no why am I doing it, because it it makes my argument simple, and you will see that. Okay, once we have these observation, proof is very simple. Okay. Okay, so now what do I want to show? My goal was to show that if you take the minimum ST cut of G prime, right, that had relation with this thing, right. Now, I will say that minimum ST cut of G prime is the same as set S which minimizes this quantity. Okay. See, I am not talking about sets here, I am just talking about the values here. Okay. Okay. So, if I want to show some equality, then as we saw earlier also, we need to show inequalities in both the directions, right. So, let us see that. Let us take any minimum ST cut, okay. Let us say this is my minimum ST cut. Let us say this, so ST cut is there, okay. Just see what are the positive nodes here. Some positive nodes, call them S star. Whatever positive nodes are there in my B star set, call them S star, okay. Remaining are where? I mean, of course, they are in A star, right. Can I have in neighborhood of, so negative neighborhood of S star here? Or in neighborhood, does not matter, negative, positive. Of course, can I have it here? Reachability, this is basically denoting the reachability set. Can I have it here? Just think for a while. Use the property that A star B star is a min ST cut. Who said no? Yeah, why?
Because the edge connecting them have been as
Infinity, right? But why is it true that your min ST cut is not infinity?
Because you can just have S.
Because you can have everything here and T here, right? Because from positive nodes you have arcs to T, right? And that is the weight of the rotation, right? Which is not infinity, right? So, there is always a non-infinity ST cut. So, minimum is of course going to be non-infinity, right? So, very good. So, I because of this, this lies in your B star, right? Okay. So, this edge is going to contribute in my ST cut, right? This edge is going to contribute in my ST cut. So, whatever is the cut value, at least these two are there, right? So, I know that cut of A star B star is greater than equal to weight of nodes here and the weight of nodes here, correct? Because weight of those nodes is the capacity on these arcs, correct? There might be other arcs as well, that is why we are saying cut of A star B star is greater than equal to this value, okay? Okay. So, I can also say that with respect to if one particular S star this is true, then it is also with respect to the minimum, right. Okay. So, you see we have proved one direction, that A star of B star was my min cut. So, we have proved that min ST cut is greater than or equal to this quantity. See, it was easy by reducing it to, by just applying some observations, right. Are you all convinced that we have proved one direction, one inequality? Okay, good. Let us show the other. This is also similar, I mean it is easy. Let us say S is some subset of P which minimizes actually this quantity, okay. That is the particular S I am talking about. Let us construct a cut, okay. So, let us construct a cut partition AB, S is here, T is there. Let us put S there in B, okay. In neighborhood there, remaining negative nodes you can put here, P minus S, I mean remaining you put here. We have arcs from here to here. Do I have arc from here to here? No, right, because otherwise these vertices will also reach to S, right, but this is a reachability set, right. So, I do not have arc from here to there, correct, right, okay. And I have arc from, similarly I do not have arc from here to here, I do not have arc from there to there, right. Negative nodes anyway do not have arc to T, correct, okay. So, P minus S to T also we will have arcs, okay, okay. So, cut value of this particular partition is weight of these nodes plus weight of these nodes, right. Cut of this particular partition has this thing, right. So, min cut can only be less. So, we have proved. Right. So, we have proved both the directions. So, we have the equality, right. So, we have proved with respect to this, and this S is actually the same as what I have taken there. You can work with you can work with any S actually, that also does the job, okay. But because with respect to one S I have shown, so with respect to min also I have shown, okay. Is that clear? Okay. So, what are the main steps of this algorithm, right? We construct, of course we compute, this part is actually I missed that we, okay, no, that is fine. Sparse rotation digraph construction itself is, of course to construct sparse rotation digraph you need to compute rotations, you need to compute weight, then you add all arcs and all these things. So, this can all be done, then you construct instance of ST cut and then you find the ST cut and just do all this whatever we said, okay. If you have any questions you can ask. I am done with this algorithm. And I am not going to say any other algorithm. So,
who is this algorithm by?
This I also do not remember.
Yeah, that's
Maybe I will add a reference in the slides before I share it. So okay. So again the algorithm, so main takeaway is that there is a some nice story about rotations, right. I hope you understood the definition of rotation, right. There are only polynomially many rotations, we can compute it in polynomial time, okay. If I start with a man optimal matching, right, there is always a sequence of rotations that I can apply and reach to a desired matching, right. And then we observe something about the egalitarian matching, right. We saw that okay, what kind of rotations I want to find for the egalitarian stable matching, right. So, for that we said okay, we will define some notion of weight of rotations and then we want to find the maximum weight rotations, right. But rotation I cannot just go and apply, there is a closed set, there is a precedence relation. So, I need to find closed set of rotations, right. So, then we said that okay fine, I need to find closed set of rotation, we define notion of rotation digraph, right? And then we reduce to ST cut instance, right? And find the ST cut instance and find the closed subset. Okay, so this is a summary of the algorithm we have. Okay, okay. So you can go over the algorithm again if you want. You can ask. I'll be here only, and okay. So there are other fairness notions. We don't have time. I'll not go into it, but there are several. Okay, and I have written many more. I have definitions, but again we don't have time, so I'll not go into it. But okay, before that we say this, I wanted to say one more thing, that egalitarian stable matching in bipartite graph is polynomial time solvable. But if we go to general graphs, it is not polynomial time solvable. Okay, but there are special instances like path, cycle, for which we can find the polynomial time algorithms. Okay, and those are not using the heavy tools. You can just observe couple of things and come up with those algorithms. For cycles, okay. Path, yeah, you are right.
Cycles also, it's a bipartite.
No, I mean you can have even cycles or cycles. Yeah.
So chromatic number 2 graphs.
Huh?
Chromatic number 2 graphs.
Chromatic number 2 is bipartite, right?
Yeah, sorry. Hang on.
Cycle, why cycle is it always?
Not getting a cycle in general graphs that are chromatic number 2, they can be converted to bipartite.
That's right, right. Okay, so actually these problems comes from the economics. Okay, they don't talk about chromatic number and all, right? But you are right. If you think from the graph theory point of view, then indeed these graphs are too colorable. Okay. So yeah, so do that as an exercise. That was my main point. Okay. For cycle, I mean path, of course, as Sushmita said, that's bipartite only. But see, for path you can easily come up with even nice algorithm, like without using these heavy tools. Some very simple algorithms just by observing couple of things. Okay, so just think about it. Okay. Okay. Median I also had. So there is actually a lot of literature, and who was asking about minimizing the divorce. This is the, if I understand your question correctly, then this is the question where you are trying to minimize the number of blocking edges. Okay. Popular matching, Kavita works in this domain, like full popular matching. That's all.